Hey, Math 206 students, welcome back. I just crashed into the chalkboard there, or the whiteboard. So let's see, last time we were studying eigenvalues, eigenvectors, eigenspaces, and there's a reason for us to be interested in those. An eigenspace, if you live in an eigenspace, right? So let's say, here's the eigenspace corresponding to some eigenvalue lambda, right? So if you are a vector, say V, and you live in the eigenspace, then what happens? When you multiply by some matrix A, or V matrix A, what happens? Well, you are then a scalar multiple of the original vector, right? So it's very easy to picture how matrix multiplication behaves, right? How it transforms an eigenspace, because all it does is it stretches each of the vectors inside the eigenspace, right? So we're going to continue to be interested in this idea of eigenvalue, eigenvector, and so on. But we need to take a little step back, and we're going to work with this definition to start with. So let's take a couple of matrices A and B. So let's let A and B be n by n matrices. Now, we're going to say that they're similar, so we'll say then A is similar to B if there is an invertible matrix say capital P, such that A is equal to P inverse B times P. So it's kind of a strange definition, but this is our definition. So we'll say that A is similar to B if A can be written in this form. So there's this connection between the matrices A and B, and what's the connection, right? Multiplication of B on the left by P inverse, on the right by P, right, results in the matrix A. Now, one thing to be aware of, so let's say note, if we have this equation right here, A equal to P inverse BP, then B is equal to P inverse inverse times A times P inverse. And so, what does that tell us? If A is similar to B, then B is also similar to A, right? So now we can say, A and B are similar. Let's say it like this. The point being, here we defined it, A is similar to B if A goes on the left-hand side, and you can express it in this way. Now notice, if A is similar to B, then B is also similar to A, which means that we can just say, let's talk about these matrices as being similar. Now, it is an odd definition, but here's why we care. So let's say this: similar matrices share several, or else it's really many properties. So let's write this as a theorem. So if A is similar to B, then, and there's going to be a bunch of parts, actually this is going to go parts A through G. The first thing that's true, the determinant of A is equal to the determinant of B. So similar matrices have the same determinant. Part B, A is invertible if and only if, I'll use a double arrow for that, if and only if B is invertible. So similar matrices are either both invertible or both non-invertible. If A is invertible, then B is. If B is, then A is. If A is not, B is not, and so on. Part C, they both have the same rank. So rank of A is equal to rank of B. Part D, they both have the same nullity also. So nullity of A is equal to nullity of B. They have the same trace. Remember, we haven't talked about trace since, I don't know, one of the early days of class. So the trace of A, remember that's the sum of the diagonal entries, equals the trace of B. Part F, A and B, yeah, okay, right, they have the same characteristic polynomial, which means then that they, oh, remember the shot there, which means that they have the same eigenvalues. So we'll say, and so, the same eigenvalues. And then the last one, part G, the eigenspaces of A and B corresponding to, let's say, lambda, have the same dimension. Right? So we've got these two matrices A and B. They both have the same eigenvalue lambda, which means that they're each going to have an eigenspace, right? The eigenspace E sub lambda corresponding to A, and the eigenspace corresponding to B. Both eigenspaces will have the same dimensions, that's what I would say. Okay, and I want to just verify a couple of these facts. All right, I'm not going to prove every one of them, but let's look at why some of these are true. So, proof. First, let's just look at the proof of part A. So, now what we want to do, proof part A says that they both have the same determinant. Now, what we have, so we can say since A is equal to P inverse times B times P, we have the determinant of A equals the determinant of P inverse B P. And then we have to remember that determinants have this nice property. This is equal to determinant of P inverse times determinant of B times determinant of P. Now remember, the relationship between the determinant of B, sorry, I just saw something on my phone there, got distracted. So the determinant of P inverse is the reciprocal, right? It's 1 over the determinant of P. All right, so now we have this, and then these two cancel, and so what we're left with is determinant of B. Right? So similar matrices have the same determinant. It's an easy computation to verify that. And then I'm going to also prove part F, which for us is essentially, it's really the most important one for what we're discussing right now, is part F. And so let's look at the determinant of A minus lambda I. Remember, this is the characteristic polynomial. It's the determinant of A minus lambda I. And then we know that A is, how do I want to do this? Yeah, just substitute. So this will be B inverse, P inverse B P minus lambda I. do this? Oh, right. This is equal to the determinant of P inverse BP minus lambda times P inverse IP, right? I is equal to P inverse IP. And then I can write this as determinant of, let's make sure I make the right next step. Yep, I'm going to factor P inverse out of both sides on the left and P out of both sides on the right. So this will be P inverse times B minus lambda I times P. Right? If you just do the distributive property and multiply back, you'll end up with this step right here. And now from part A, what do we know? Well, what we have then is this matrix A minus lambda I, we've now shown, is similar to the matrix B minus lambda I, right? Because what's happening, this matrix is equal to this matrix with a P inverse on the left and a P on the right. And so from part A, this is equal to the determinant of B minus lambda I. So this is by part A. Okay, now kind of gonna take a little, I don't know, change of pace here. So when it comes to matrix multiplication is sort of a time-consuming process, right? The definition of matrix multiplication is a pain. There is one class of matrices for which matrix multiplication is very easy to work with. Diagonal ones. Diagonal matrices, for various reasons. Okay, so let's just say it this way. Diagonal matrices are easy to work with. For example, if D is diagonal, then computing the determinant is nice. So the determinant of D is easy to compute, right? Normally, right, when you compute a determinant, that's a big process, but the determinant's easy. It's also easy, so determinant is easy to compute. Raising D to a higher power, D raised to the K, is easy to compute. All right, now the lights just went out. Okay. You can walk over by the motion sensor to turn that back on. What else? Oh, eigenvalues. So eigenvalues are easily identified. Right? They're just the diagonal entries. And then one more thing, the action of D on Rn is easy to picture, right? Whenever you have an n by n matrix, so assume that D is an n by n matrix, then what is it? It behaves as a transformation of Rn, an operator on Rn. And so in the case that you've got a diagonal matrix, it's very easy to picture how it behaves. And so we talked about this idea of similarity. What we're going to be interested in then are matrices that are similar to diagonal matrices. So I guess let's write this as a definition. A matrix A, an n by n, square matrices, so an n by n matrix, capital A, is diagonalizable. Diagonalizable. If A is similar to a diagonal matrix. right? So we can't, obviously, we know that most matrices are not diagonal matrices, but those that are similar to diagonal matrices are the ones that we're going to be interested in. They have lots of nice properties. According to that previous theorem, right, many of the computations, right, and the characteristics of the diagonal matrix will be much like the characteristics of the diagonal matrix. I think I said that pretty. Let me say that a little better. Diagonalizable matrices behave much like, or we can understand them, get a feel for how they behave by understanding how the diagonal matrix that it's similar to behaves. So just to kind of elaborate on what it means to be diagonalizable, let's say it this way. In other words, an A is diagonalizable if there exists an invertible matrix P and a diagonal matrix capital D, such that D is equal to P inverse A times P. Okay, so somehow it's good, right? Being a diagonal matrix, being a diagonalizable matrix is a good thing, right? It has some of the properties, it behaves much like, or as close as you can get, to a diagonal matrix. So it'd be nice to know when this occurs, right? When is a matrix diagonalizable? And so this next theorem is going to answer that question for us. An n by n matrix, capital A, is diagonalizable if and only if A has n linearly independent eigenvectors. All right, that's kind of a strange thing that just showed up, right? We were talking about eigenvectors last time, and now, right in the middle, or as we're discussing this seemingly unrelated topic of diagonalizability, suddenly this notion of eigenvectors shows up. Now, one thing to remember, so we've got an n by n matrix, which means that it operates on Rn. So the eigenvectors are living in Rn. If you have n linearly independent vectors, forget the eigen part for a second, anytime you have n linearly independent vectors in Rn, you know that they form a basis. So a way to restate this, so let's say restated, A is diagonalizable if and only if the eigenvectors, or let's say better, Rn has a basis consisting of eigenvectors of capital A. So that's a nice way to think about it. Diagonalizability corresponds exactly to bases for Rn consisting of eigenvectors. And so this is an important theorem, and we actually want to go through the proof because the proof is going to tell us exactly how to decide whether we've got a diagonalizable matrix, and when it's diagonalizable, we will know exactly who this matrix P is. So I'm going to go through the proof. And so it's an if and only if statement, so there's actually two directions that we want to prove. So what I'm going to do first is assume that A is diagonalizable. So let's assume that D equals P inverse A P, where D is this diagonal matrix, and on the diagonal, so I'm going to write it out, lambda 1 down to lambda n, zeros everywhere off of the diagonal. So then, if I multiply both sides of this equation by P inverse on the left, what we'll get is P D is equal to A times P. If we write, so I want to express P in terms of its column, so if we write P equal to the matrix whose first column is P1 up through last column Pn, then let's see what we have. So we have P times D. Let's see, if you multiply by a diagonal matrix, what does that do? It multiplies each of the columns, right? If you multiply on the right by a diagonal matrix, what it does, it has the effect of multiplying each of the columns by the corresponding diagonal entry. And so what we would have is that P times D is equal to lambda 1 times P1, that's the first column, up through lambda n times P sub n. So it follows that, so let's see, what do we have? We have A times P, make sure I get this right. Right, so this tells me, so it follows that A times P1 is equal to lambda 1 times P1, all the way up through A times P sub n is equal to lambda times P sub n. Just thinking about how matrix multiplication works, right? What we have is A times P is the matrix whose first column is A times P1. Next one is A times P2 and so on. And then what we have is by setting them equal to each other, it tells us that A times P1 has to equal the first column of P times D. A times P2 has to equal the second column of P times D, and so on. Now what? So since P is invertible, it follows that follows that what? Oh yeah, that this set right here, P1 up through Pn, is linearly independent. So we've got a linearly independent collection of vectors, and this line right there shows that each one of those vectors is an eigenvector. So what do we have? A linearly independent collection, n of them, n linearly independent eigenvectors. Okay, so there's the forward direction. Now we want to look at the reverse direction. So let's say it like this. Oops, I just lost my marker here. I think it's right about there. So let's see. In the reverse direction, let's let this collection P1 up through P sub n. This is going to be a basis. So let this be a basis of eigenvectors for Rn with corresponding eigenvalues. So I'm going to write it like this with lambda, we'll say lambda sub I, corresponding to P sub I, right? So lambda I is the eigenvalue corresponding to P sub I. Now, let's write out, so let's say letting P equal the matrix consisting of the columns, or whose columns are these eigenvectors right here, and D equal to lambda 1, so it's the diagonal matrix that looks like that, then you can actually just verify it, just multiply it out. So we get D equal to P inverse times A times P. Okay, so that concludes the proof of the theorem. So this proof now tells us everything that we need to know. And now I'd like to summarize. So let's say summarizing. To diagonalize capital A, which is an n by n matrix. The first step, what we do is we want to find the eigenvalues. So let's find the eigenvalues. Find the eigenvalues. Let's call them, say, lambda 1 up through lambda sub k. Notice this k is not necessarily the same as n, right? A might be a 6 by 6 matrix, but it only has 3 distinct eigenvalues. Let's say 1, -2, and 7. Right? It doesn't have to have n distinct eigenvalues. So there's the first step. The next step is to find, let's find a basis for each eigenspace. E sub lambda I, right? So there will be an eigenspace E sub lambda 1. Find a basis. We learned how to do that last time, right? Find the eigenvectors. Now, combine, so the third step, combine all eigenvectors found in step 2, right? So each time when you find a basis, there's going to be some eigenvectors for E sub lambda 1. Then there'll be some basis, which is more eigenvectors for E sub lambda 2. Lump all those into one set. And keep the order also. So let's say preserve the order. Now, once we've done this, if there are less, and when I say preserve the order, meaning if we called, we've got lambda sub 1, and then there's going to be eigenvectors. The eigenvectors corresponding to lambda sub 1 should be in the first chunk, and then the eigenvalues corresponding to lambda 2 should be in the next set, and so on. If there are less than n, then A is not diagonalizable. So we find all these find the basis vectors for each eigenspace, lump them all together. If we have fewer than n in that final list right there, then our matrix is not diagonalizable. If it is, right? So if we have exactly n, so if there are n, then D is going to be, and this is a little weird to write this, it'll become more apparent once I do an example. But now I'm going to write it as lambda 1 up through lambda n, where we might repeat ourselves, right? If there are 3 eigenvectors, right? So if there's a P1, a P2, and a P3, those are the eigenvectors corresponding to lambda 1. Then I'm going to write lambda 1 along this diagonal 3 times. Right? So there might be, there very likely will be some repeats along this diagonal. Let's see, that and the matrix P is P1 up through P sub n, where these P's right here are the eigenvectors in order, right, that you found in each of in step 2. Okay, so here's what I'm going to do. We're going to stop here, right? There won't be any homework for this that corresponds to this until we actually get to the next section. Yeah, I think that's true. Yeah, so I'll just assign all the homework when I finish this. So in the next lecture, what I'm going to do is a bunch of examples of diagonalizing matrices. Okay, so this is a good place to stop here.